sure we'll So first off, Comet Neowise. Everybody should be trying to take a look at that. Biggest thing in the sky so far. It's visible for the next few evenings. It's low in the northwest sky. So your house across the street may be blocking it, a tree, maybe a mountain could be blocking it. So you've got to find a nice dark sky that you can see the horizon, the low horizon. It's faint, best seen at dark, in a dark sky with binoculars. Naked eye, it's tough. If you know what you're looking for in a dark sky, you can make it out with the naked eye, but binoculars, I'm able to see it in my backyard here in East Mesa. And of course, those with telescopes can see it much better. But those dramatic pictures, like the one in the upper right that you see, those are taken with a camera and a few seconds of exposure. Sometimes you see pictures in which they were stacked. So don't expect it to be that clear when you go out there and look for it naked eye or with binoculars. It'll be a little bit dimmer.
Hey, Gordon, there's a quick question.
Yeah.
Do you know who took that picture in the corner?
No, this was just directly off the internet.
Okay.
It seems like there's hundreds of pictures on the internet. In fact, our EVAC Facebook page has quite a few pictures of our EVAC members that they took and posted on the Facebook. In fact, some of them had said what camera they used, what the exposures were. So visit our Facebook page and then it'll give you some more information. I just picked that picture out because it kind of shows the elevation above the horizon, which now I think probably is about 15, maybe 20 degrees when we're starting to be able to see it. But remember, it's going to be faint, and it's not going to be like those pictures unless you take your own pictures. Now it's going to start getting higher each evening, but it's starting to drift away from the sun, so it'll be getting dimmer. So higher, easier to see, yet dimmer, more difficult to see, and it's really only going to be visible for about the next week. But it has an orbital period of 6,800 years. 6,800 years. Now, the last time it passed by Earth, there was no written human history. So this thing has a long period. The next time, well, hopefully the Earth will still be around, but 6,800 years. Wow. Anyway, y'all got to take a look at this. This is fantastic when you can see it. This is a big thing for astronomers. It gives you chills. So everybody go out there and try to find it, at least see it. We don't know when the next time a visible comet's going to be in the sky. I think the last time was maybe 15 years ago, I guess, when we last saw a visible comet up. Okay, so welcome everyone. Of course, live long and prosper. The agenda for tonight. We'll do a welcome, which is right now. Welcome, everybody. And this is our Zoom meeting online. This is really the only meetings that we have. We started this is our third one now. We'll be doing this until it gets safe enough that we can start our regular in-person meetings. So introductions, this is your leadership team. So club members, your leadership team is still working. The club is still viable, it's still operating. We have bills to pay. There's things going on. There's a newsletter to write that we publish. We have a website that we keep up. Our board of directors are still making decisions. We're still paying the bills. So our club is still operating, and this is our leadership team. And Tom Mosden is the one who does all of our online engineering, so to speak. So thank you, Tom. In some current business, Remember now, all EVAC personal contact events remain canceled. That's everything. Star parties and outreach events, library events, meetings. Greco Observatory is still closed. Oh, that's heartbreaking for all of the Greco volunteers that liked so much hearing all those oh wows in the evening. And again, we really don't know when we're going to open up yet. Of course, that's a decision that the board of directors collectively will make, and we'll just have to make sure that there's enough safety procedures in place. And we don't know what that's going to be right now. So the meetings that we do now, the online meetings, that's all we really have going. And just a reminder that things like the Picket Post Trailhead, other personal type gatherings, they're not EVAC sponsored or endorsed because still the club is not endorsing any in-person gatherings. Of course, any of those gatherings that you do decide to do, those are personal decisions. And of course, you know, please guys take the appropriate precautions because we want to see you come back when our club opens back up. Member presentations. Remember too that these meetings follow the same format as what we had during the in-person meetings. So there's a member presentation, any kind of current business, we have a main speaker. So the same thing is going on as we would if we were in person, except we don't have the snack bar behind us that Jana Cody always provided so much for us. So member presentations. We have one tonight. We have a couple of them that, a couple people that want to do some. If you want to do a member presentation, please get a hold of me. And you can get a hold of me through the website, through our EVAC website. And just click on the EVAC president. Let me know that you're interested. And we'll chat with you, see if there's any questions that we have. We can either do before the regular meeting, we can do a little practice run with you, make sure that you're comfortable with it. But please, we're keeping the meetings going, and member presentations are a big part of our meetings. Now, fortunately, we have great main presenters who are talking the science aspect, the industry, latest type of things going on with the industry. Fantastic that we have those lined up. The member presentations now, they're on the other end of the spectrum. They're things that you personally have done. Maybe you want to show pictures that you took, show us some equipment that you have, and you would be helping out the other end of the spectrum. Maybe those people just starting out, or those people that are interested in the things that they can do. So we have the whole spectrum covered as long as we have member presentations represented. So please, if you have any ideas and want to join in member presentations, contact me through the EVAC president link. And speaking of member presentations, Claude Haynes, who's also our Greco manager, he has our member presentation coming up right now. So I'll let him take on over.
Okay, let me unmute and do the magic of screen share.
And I will stop mine.
Yes. And now, hoping. So back up one. So do you see my screen, Tom?
Not yet.
Okay.
You have to say okay after you selected it.
Let's try one more time. I'm clicking share and it's not. Let's try that.
That's looking better, yep.
Now.
Yep, you got it.
All right, let me go back one. Come on, mouse, behave. There. Okay, so And if you are seeing our screens, you don't necessarily need to see me. You can click the little minimize and hide the thumbnail so you'll get the full picture. So tonight I'm going to be talking about variable constellation. We're familiar with variable stars, but there is a new constellation in the night sky that varies in brightness as well as position. These are communication satellites from SpaceX Starlink program. There are hundreds in the sky now, with many more to follow. They've been in the news lately, and they will have an impact on astronomy both professionally and as a hobby. Uh, this talk comes from a seminar held by the Astronomical League. The public sessions were conducted over Zoom, and they were on June 29th and 30th. Many of the organizing committee presented data along with the International Dark Sky Association and SpaceX itself. The group is working on several white papers to document the issues and offer suggestions on mitigation.
Hey, Claude.
Yeah.
We are seeing your next slide.
Okay. Then let me do display settings and swap. How's that? Is
Yes,
that better?
that's it.
Thank you. Okay. So let's go with that. The presentation was eye-opening concerning the impact to astronomers, and both amateur and professional, with so many satellites now and soon to be in orbit. I also don't want to seem like Chicken Little. The sky isn't falling, but it is filling up. As an aside, Chicken Little is doing well, writing press releases for any asteroid that comes within 6 lunar distances of Earth. I'm likely to upset you, and I am going to depress you a bit. Sorry, please don't shoot the messenger. The major alarm bells rang during testing for the Vera Rubin Observatory being built in Chile. This is a sample image taken from Hawaii that shows multiple satellite trails across the many segments of the camera during testing on a 3-meter telescope. The Vera Rubin Observatory is currently under construction in Chile, and you may be more familiar with its original name, the Large Synoptic Survey Telescope. It is scheduled for first light late in 2020. May miss that a little now because of the stoppage of construction for a little time during the COVID-19 issue, but it is winter there, so this was not their prime building time anyway. Full operation is scheduled in October of 2022. It's named for Dr. Vera Rubin, shown here working at Kitt Peak National Observatory, who was instrumental in studying the distance and speed of galaxies. Her calculations led to theories on dark matter and dark energy. The telescope mirror was cast at the Keras Mirror Lab in Tucson in 2008. Some of you have been on the recent outing with Ken that he recently arranged. I do recommend visiting if you haven't been. I'm not sure what their schedule is right now, but it is an interesting place. The mirror is unique in that it has 2 figures. One kind of the standard figure, and then in the center a much deeper figure to give it a wide field of view. The mirror design combined with lenses for the camera reduces spherical aberration across a really wide field. And you can see that in the camera. It is made up of many segments to create a 3.2 gigapixel prime focus and will take 15-second exposures every 20 seconds. The image of the moon is superimposed to indicate how wide a field the telescope is looking at. This produces a huge amount of data, which will be sent to partnering observatories for confirmation, all hopefully automatically. Now, the goals of the observatory are to study dark matter and dark energy, so it's appropriate it was named for Dr. Rubin. Mapping small objects, especially near-Earth objects, they're trying to, Congress has mandated they find at least 90% of all of the asteroids, especially anything that could pose a danger to the Earth. Detecting transient optical events like supernovas, mapping the Milky Way over a 10-year mission, and then study gravitational lensing and gravitational wave effects, which should be very interesting with the telescope. Now, for SpaceX, they're launching satellites about 60 at a time, several times a year, to create a constellation of satellites to provide internet connectivity worldwide. And they're kind of like pizza boxes stacked in the nose cone. Satellites are in low Earth orbit at about 550 kilometers. Normally, satellites are about 1,000 kilometers or so. The ISS orbit's about 400 kilometers, 250 miles. Geosynchronous satellites are way out at 36,000 kilometers. Keeping space clean, if you're reading this slide, means that they deorbit dead satellites, not that they don't do other collateral damage. The satellites are solar powered, and the base has a number of phase array antennas. Eventually, the satellites are designed to communicate with each other via laser. They also feature an ion propulsion system. Satellites are launched into a lower orbit, and then they are boosted into their final position. Obviously, they are brighter at lower altitudes. They also have autonomous collision avoidance built into the satellite. Tom probably has had some experience with that on his Tesla. And the reason they need to have this is because there will eventually be thousands of them, 12,000 to begin with, perhaps 20,000 more. So why is this happening? Well, it's because Elon Musk wants to personally drive his Tesla to Mars. The revenue stream from Starlink will be much larger than SpaceX alone. But the real reason is that there are a lot of places without internet access or reliable communications. These rural locations cover wide geographic areas where it's hard to build and maintain infrastructure. But SpaceX is primarily targeting the US and Canada for its initial rollout, and you can see there are still lots of spots with limited access, especially in Canada. The Rural Access Project is being driven by the US and Canadian governments to promote education and commerce. And as we have seen from the need for high-speed internet during the pandemic lockdown, this is something that would be worthwhile. This is an APOD picture from December 2019 showing the trails of Starlink satellites. This was taken in Chile. Perversely, some people enjoy tracking the trails, just like we used to look for iridium flares, if you remember those. On my phone, I have Heavens Above installed, and there are also other apps that track Starlink. As you can see, their visibility is about 3 to 4 magnitude. You can also track the ISS passes with this app. So for astronomy, many of you have taken wonderful photos and shared them to the community. Thanks, Bernard and others. I'm sure you've had to erase trails from images or delete ones that had trails from a stacked image. That is going to be much harder with so many trails. Thinking about the goals of the Vera Rubin telescope and the extreme wide field of view, think about their mission to search for near-Earth objects and transient events. By its very nature, the glint from a satellite is a transient event. The problem was nowhere on the radar for scientists in the past decadal surveys. Now, these decadal surveys are every 10 years on the even years. This is where scientists beg the National Science Foundation and others for funding of long-term research. In the 2020 survey, there were numerous proposals related to solving for this. So for photo mitigation, I'm going to summarize a bunch of things quickly. I know this may raise some questions. You can send chat to Tom if you have a question. Hopefully it makes sense. The Vera Rubin hoped that data could be automated and any transients would be sent for follow-up. They are going to be sending buckets. This is a fire hose of data with that large a camera, taking pictures every 15 second exposures every 20 seconds. And they had hoped that they would have an ability to send out reports to the partner observers and say, hey, we saw something that looked like it could be a supernova, go check this out. But the issue is with these satellite trails, there's just going to be an awful lot of noise and issues. The The session discussed an algorithm that could eliminate the trails from the image. They're pretty obvious. But with so many camera segments, there is an issue of crosstalk between the amplifiers, which produces parallel information in the trails, which is harder to eliminate that ghost noise. You also have the problem that eliminating the trails eliminates the data. The very thing that you're looking for could be hidden in that line across the screen. The trails for satellites at 500 kilometers are also slightly out of focus due to the low orbit when your telescope is, your camera is set at infinity, making them a bit wide, but perhaps easier to deal with because of that. Another mitigation may be able to just not take a picture or automatically toss it out if you know when the satellite will be crossing. That requires really accurate positioning data for the satellites. The bigger problem is the core research mission. The Vera Rubin, one of its major missions, was designed to look for the near-Earth objects. Those are best viewed at twilight and just before sunrise, and you're not only looking through more atmosphere, but now a maze of satellites concentrated as they rise into view. SpaceX is working on mitigation for the satellites. They can control the solar array to produce less reflected light, often close to the horizon. They recently darkened the bottom of the satellites, but that caused some heat problems. And so the next generation will include a visor to block reflections. The goal from the Vera Rubin team was to get the brightness level below magnitude 7. That theoretically will minimize the impact. But SpaceX is not alone. We are just at the tip of a very large iceberg. SpaceX is actively testing. They are starting with 12,000, but have requested 20,000 more. The reason for so many satellites is to reduce latency and thus have increased network speed. OneWeb went bankrupt, but the week after the conference, the United Kingdom gave them £500 million as to become a partner and bail them out. This is primarily for rural communication, but may also be for military use, especially since after Brexit, they are out of the shared EU projects. So Amazon and Telesat are not at the same level of testing, but it's one of those situations where there are a lot of players. Don't just think that Starlink is the only issue here. Now, many of us are used to seeing satellites fade as they fall into the shadow of the Earth, especially the ISS. Starlink satellites will have less reflectivity, but not dark at 500 kilometers. OneNet satellites at 1,500 kilometers will almost always be above the shadow, and they are in better focus. While the session focused on Starlink, other satellites in higher orbits may pose greater or different problems. Now, I know many of you are thinking the clear night sky is a human right, and I agree with you, but so is privacy, and we give that up every time we log on to the internet. If you haven't read it, I recommend Neil deGrasse Tyson's book of Accessory to War. It's well researched by his co-author Avis Lang. The current space treaty that was written by the US and the Soviet Union was written with deliberate holes. Don't count on the government to help, but it is possible that intervention like that could eventually occur. So, the good. SpaceX is trying to mitigate some of the damage, and they were really cute. These are our people. They love astronomy. They love space. They did all sorts of Star Trek and Star Wars illusions, but I don't know that they'll be able to really solve the difference. The bad, there are other companies and they may not care. While this is primarily being controlled by the United States and the Federal Communications Commission, other players, other countries, China, Russia, India, Iran, they may launch their own constellations. These are commercial enterprises with allegiance to their shareholders and governments, not astronomy per se. For those of you who are old enough to remember Tom Lehrer and his parody satirical songs, I'm reminded of one of his classic lyrics. Once the missiles go up, who knows where they come down? That's not my department, says Werner von Braun. The Ugly. This is a secondary movie reference. You may be able to stop a few zombies during the apocalypse, but if there are thousands of zombies, you're pretty much sweetbread stew. Finally, many of you will recognize this spot. Through countless millennia, our ancestors have gazed up into the heavens, tracking the movement of the sun, moon, planets, connecting the dots to tell their history, religion, myths, marking the times to sow and reap, celebrating equinox, solstice, and eclipses. Sadly, I have come to the realization that now I am among the last generations of humankind to be able to say I was able to gaze upon an uncluttered night sky. And with that, back to you, Gordon.
Before we go back to Gordon, Claude, Mr. Cherry Sunshine, there's a question. It's why are near-Earth objects best viewed before sunrise, or whatever time you said it was?
It's because they are going to, like comets, they're going to be a little more visible and more illuminated. So it's just a matter of brightness. As they're coming into the sunlight, they're going to be brighter.
Okay, thank you.
Okay, and Gordon, your president, and can you hear me?
Can you unshare me, Tom? Because
I think so.
I don't see a.
Yeah, there we go. I stopped.
Okay, thank you.
There we go. And let's see. Can you guys hear me? This is Gordon. Can you guys hear me?
Yes.
Yes. Yes.
Oh, okay, good, good. What I want to do is just remind everyone that there is below or maybe above, depending on your platform, there's a chat button and a Q&A button. So the chat, go ahead and jump on in there and chat around with other attendees, panelists. It's kind of, if you want to make a statement or a funny, go ahead and join in on the meeting by all means. The Q&A is if you actually have a question about the presentation. So instead of breaking into the presentations, type your question in the Q&A button down there on the bottom, and then either Tom or myself or maybe the presenter afterwards can answer that question. So Tom, I will give it back to you for our main presentation.
Okay, I will introduce our main speaker, and instead of reading a bunch of lines of titles and where she went to school and what she's working on, I'll do it a little bit more interactively so you might actually remember it. I know when people read introductions verbally, I don't remember what they've said. So let's see, I want to share my screen. There. So what I do when I want to introduce a speaker is I go to their website and see what they think is important about themselves that they'd like to tell visitors. So first of all, she's in NASA Exoplanet Science Institute, at there, in the Deputy Science Lead at NASA's Exoplanet Archive, research scientist at NASA Exoplanet Science Institute, and she won the Griffith University Outstanding Young Alumnus in 2018. And this one I like a lot. A mother of twin tornadoes. Those of us who have had kids will remember what a bundle of energy they can be at that age. So congratulations there. A few things on her research: exoplanets, exoplanet occurrence rates, catalogs, and among other things, light curve software, exoplanet atmospheres, and variable stars. A lot on exoplanets, which is why we're hearing about exoplanets. And Jessie's doing a tremendous job on mentoring. It's very important to her. And as we found out earlier in the beginning, I'm not sure everyone was on or not, but she had a luncheon Zoom meeting with a few girls that were interested in becoming or entering the STEM field, what it's like, what you can expect, tips and things like that. So that went really well. So maybe just going up to the slightly more boring aspects. If you click on their CV, it tells you just a little bit more about them. And we can see that I believe you grew up in Australia, or at least you went to school there. Yeah. And did the postdoc 2008 to 2010, and then very nice 2010 to 13, a staff scientist at the Kepler Science Office. And then present research scientist at NASA Exoplanet Archive, lead scientist. And various awards, very nice, a nice list of them. And if you're interested in some of our publications, they're listed here, and you can go look them up for more information. This one to me seems sort of prestigious, the 2020 invited talk on the National Academy of Sciences Astronomy Decadal Survey Panel, because they sort of set the agenda for what's important to astronomy for the next 10 years. So well done on being invited there. So I will stop talking, and I will let Dr. Jessie pick it up from here.
Thank you so much, Tom. That was a very kind introduction. Yeah, the 2020 talk list is going to look pretty thin, though. All the travel's been stopped, and everybody's colloquia of, rush to go online. But I will say, a silver lining of all of these things going online is, I've given talks to the local amateur astronomical clubs around LA, but the fact that we've gone virtual means my geographical footprint that I could give talks to is greatly expanded. So this is the first time I've given a talk in Arizona. I'm very excited. Thank you for inviting me. You guys have a very storied history in astronomy and in your contributions. So I'm excited to talk to you guys, Arizonan astronomers. Let me see if I can get my screen going. Okay, can you see my title slide?
Yes, looks great.
Okay, fantastic. Okay, so tonight's talk is called On the Road to a Billion Planets, and it has a little bit of a hidden subtitle, which is On the Road to a Billion Killer Planets, and I'll explain a little bit more about that. So what are exoplanets? That's what I'm here to talk about tonight, are exoplanets. So this is a schematic of our solar system, not to scale. We have one star, and that actually it becomes important later. We have one star. We have 8 planets. I know. I was too young to vote on Pluto, so I can't take any credit or blame for that decision. 8 planets. We also have dwarf planets, which is the new bucket that they invented to put Pluto and all of Pluto's new friends in when they realized they didn't look like the other 8 planets, so dwarf planets. We also have minor planets, which is basically everything in the solar system that's bigger than a grain of dust that we've managed to catalog. So the dwarf planets, the asteroids, the Trojans and Centaurs and Kuiper Belt objects and Trans-Neptunian objects. We have a whole ton of things. There's over 700,000 things that we've identified and are tracking in our solar system. Space is big, but there's a lot of stuff out there. But what are exoplanets? So exoplanets are planets around other stars. So we'll walk through this idea a little bit more. So 2,500 years ago, the Greek philosophers were talking about the Earth. And they were talking about the Earth as a really abstract thing that exists in the way of Greek philosophers when they have this idea and they just hypotheticalize it to death. They were talking about the Earth. And they wanted to know whether it was unique or whether it was common, whether there could be other Earths out there. And again, they were doing this in the purely abstract. They were just like, could there be more than one Earth, or is Earth purely unique? And Plato and Aristotle actually argued that the Earth itself was unique, that there was nothing else like the Earth. Let's fast forward a few thousand years. Okay, so we're in 1592, which is the Renaissance. So the Renaissance was a really exciting time to be a mathematician in Italy, as Giordano Bruno was. It was not a good time to be a heretic against the church, which Giordano Bruno also was. But one of the things that he did, this Italian mathematician, was to think about planets around other stars. And I'm going to read this quote from him. there are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system. So this was, you know, Ceres, and then not Ceres, and then Neptune, and then Pluto, and then not Pluto. So 500 years ago, there were 7. So he comes to this idea that there are going to be planets around other stars. There's nothing special about our sun. Other suns might have planets around them too, and he expects that they do. One thing that Giordano Bruno really crystallizes is this is like one of the first times it's written down, that it's going to be hard to find them because the stars are so bright and the planets that are orbiting them are so dim and so small and so light in weight. There's just, you know, compared to stars, they're so infinitesimally small. And so he's one of the first people that's like, you know, I think they're out there, but I also think they're going to be really hard to find. Okay, let's fast forward again. So now we're in the middle of the 20th century. And astronomer Otto Struve thinks about this for a while. You know, a lot of astronomers have been thinking about it. How do we detect these things? If they exist, if planets really exist around other stars, what are some ways we might be able to detect them? So at this point, so in the 1950s, binary stars were well known. You could observe a star and you could see that the star was coming towards you and going away from you and coming towards you and going away from you by looking at the star's spectrum. The light from the star would be blue shifted towards you and then red shifted away from you. So we already knew how to do that for binary stars. So Otto Struve comes up with this idea. He's like, okay, what if you take one of the stars out and put a giant planet there instead? So the giant planet would have to be really close to the star. So just, you know, a few days, orbiting around that star every few days. But the amount of wobble that that planet induced on the star might be detectable. Like it might just be big enough to detectable if that planet was really close. And basically everybody laughed him out of the room. They were like, you know, how would you get a gas giant in a 2 or 3 day orbit around a star? Like we know how solar systems formed. We have one. The gas giants are all miles away out in the burbs of the solar system. None of them are up close. So he has this idea how they could be detected, but everybody thinks, well, that kind of planet doesn't exist. So let's fast forward 40 more years. And in 1995, the first planet is found orbiting an ordinary star like our sun using this method, this wobble method that Struve proposed. And it was a hot Jupiter. I'm going to explain a little bit more what they are, but it was a gas giant orbiting its star in just a few days. So after 40 years, he was finally vindicated. And people who are interested in bibliometrics, which is, you know, measuring the impact of different published papers and everything. So between 1952 and 1995, his paper had, I think, 9 citations. It was less than 10, very few citations. Since then, since 1995, it has had more than 100. So everybody was like, wait, this guy, this idea, this actually worked. So he was finally vindicated. So yes, in 1995, after literally thousands of years of thinking about this problem, we finally found planets orbiting stars like the sun. Since then, there's been an incredible boon in the number of exoplanets that we've found. So this is a tweet for people who don't use Twitter. And this is me a few years ago, noting that if you plot the number of exoplanets with time, I think now that we're in a global pandemic, everybody knows what an exponential curve looks like. You've seen so many of them in the news over the last 6 months. So this was a few years ago, and I noted that this looked like an exponential rise. And I asked, is there a Moore's law equivalent for exoplanet? So Moore's law is this idea that computing processing speed is doubling about every 2 years. And I was asking, is there an equivalent for exoplanets? Like at what rate are exoplanets doubling? And one of my colleagues responded, and he did the clever thing of plotting this on a log-log plot instead of a linear plot, and fitting this straight line up the diagonal and saying, yes, it is exponential. And the doubling time is about every 27 months. So just over every 2 years, we've discovered twice as many planets as we knew before, which is wild. And he made this prediction. If this kept going, if this exponential rate of discovery kept going, we'd hit 1 million known exoplanets in 2034 and 1 billion known exoplanets in 2057. So that's where the title of my talk comes from. We're on the way to knowing about 1 billion of our neighbors in the next few decades, which is wild. So I dubbed this Marmajek's law after Eric Marmajek, who was the person who came up with it. And I'd really like to make that name stick. So if you can just leave tonight's talk and go out and just pop it into conversation spontaneously over the next few days, let's see if we can get it going. I really want it to stick. All right, so what have we found? So I've said we've found thousands of planets. We've got over 4,000 planets now. What do they look like? Before 2010, this is what the distribution of planets look like. So what I'm plotting on the x-axis here is the orbital period of the planet. So it's a year. So Earth's year is 365 days. So you go 100, 200, and 300. So here's 365. And basically what that axis is, if you go this way, you're further away from the star. So you're getting colder as you go to the right. On the y-axis, I'm plotting the size of the planet relative to the size of Earth. So here's 1 Earth radius. So if you go out here, here's Earth at 1 Earth radius in 365 days. And in fact, these magenta squares are the inner solar system planets in our solar system. So you've got Mercury, Venus, Earth, and Mars. And these are the exoplanets. And what you can see is that they look nothing like our solar system. It's so interesting. Before we discovered exoplanets, we only had one solar system to work from. So all of our theories of how solar systems formed, how planets formed, how they migrated, were all predicated on replicating our solar system. If your theory couldn't create, nicely spaced out rocky planets and then a gap and then some gas giants and then past the snow line, some ice giants, then it was wrong and you went back to the drawing board. But what we've been discovering is that you go out and look at the universe around you and it's much more imaginative than we are. So let's look at what we found. So this one is, so again, this axis is basically bigger. If you go up, you're bigger. So Jupiter is here at about 11 times the size of Earth, and Neptune is here at about 4 times the size of Earth. So you can see mostly what we had discovered were Jupiter-sized things and bigger, orbiting 1, 2, 3 days around their star. So these are these hot Jupiters that Otto Struve predicted that we'd be able to detect. And they're the easiest to detect because they're biggest and they're closest to the star, which means that the signal that they induce on the star is big enough for us to see. So this is what the picture looked like in 2010. A bunch of hot Jupiters, some slightly cooler Jupiters, and some slightly hotter, smaller planets. This is what it looked like in 2019. And what you can see is that we've really filled in this gap between these hot Jupiters up here and the inner solar system planets down here. We've got this whole glut of thousands of planets, and they're in these multi-planet systems. So a lot of the hot Jupiters are in single planet systems, which is really interesting. That's a clue as to how they form. And then there's a lot of these smaller planets that are in multi-planet systems, 2 to 4 planets, 5 to 8 planets, and we have our solar system. So what happened? What happened before 2010 and last year? Well, what happened was the Kepler mission. So as Tom mentioned in the introduction, I was a Kepler staff scientist for a few years. I joined the mission about a year after launch. It was launched in 2009. It's a 1-meter optical telescope. It's unfortunately ran out of fuel in 2018, so it's no longer operating. But from 2009 to 2013, it observed the Kepler field, what we call the Kepler field. It's this patch of sky here next to the constellation Cygnus, between Cygnus and Lyra, basically. So here's Vega and there's Deneb. So it's between Vega and Deneb. So if you look at this patch of sky next time you guys are out, you might be socially distanced sky watching for a while yet, but when you go out and look at this patch of sky, there are literally thousands of known planets just in this little patch of sky. It's about 10 degrees by 10 degrees. And we've found literally thousands of planets in there. But how did we find them? Let's see if we can get this going. Okay. We found them using the transit method. So let me explain what that is. So this is an animation showing a system called TRAPPIST-1. So TRAPPIST-1 is the name of this star in the middle. It's a very cool, very small red dwarf star. It's only about 8% the mass of our sun, which is almost as small as you can get and still be a star. If you get much smaller, you don't have enough mass to start fusing hydrogen and helium in the center. So let's go back to the star. So these 7 planets orbiting it, we've discovered 7 rocky planets around TRAPPIST-1. And the thing is, rocky planets are tiny. They're really hard to see. And if the angle was like this, if we were looking at TRAPPIST-1 and these planets were all angled like this, we would never be able to detect them. But sometimes we get lucky and the system is actually lined up like this. So those 7 planets are still orbiting the star, but we're exactly looking edge on to this system. And what you can see is that every time a planet goes in front of the star, it blocks some of the light. So what I'm showing on the bottom half is basically a brightness measurement of the star. We just measure the brightness of the star over and over and over again, and we wait and we wait. And what you want to see are these dips when a planet goes in front of the star. This here is a flare. M dwarfs, these small cool red stars, are very active and they flare a lot, which is not great. We'll talk about that a bit more. But what you want to see are these dips. And when you see so many like this, you know it's a multi-planet system with lots of small planets. So what do you get from transits? I'll pause this here. So here's 2 transits of the planet B. So this is the innermost planet. So the distance between these 2 planets, the difference in time between here and here is that planet's year. It took that long for it to go around. And for B, it's less than 2 days. It goes around in a very short amount of time. The other piece of information you get from the transits is the depth. So bigger planets block more light. Let's go on a little bit more. Here's one of D. Bigger planets block more light, so the transits will be deeper, and smaller planets block a littler amount of light, so the transits will be shallower. So just by measuring the brightness of the star over and over and over again, you can find the year of the number of planets going around it, the years of the planets going around it, and the sizes, the radii of the planets going around them. And that's all you get. You basically get all that information for free just by measuring the brightness of the star. So the actual measurement is kind of boring. It's just measure the brightness of the star over and over and over again. If any of you guys have done like variable star challenges or something where you're going out trying to detect variability, it's that kind of thing, but on a much, much more precise scale. These dips are, you know, in the hundreds of parts per million, so much lower than the sensitivity of a brightness change you could see with a human eye, which is why we have to send a telescope to space to do it. Okay, let's go on. Okay, so the goal of the Kepler mission, when we launched the Kepler mission in 2009, we had one primary goal, which is to work out how common planets like the Earth were. You know, the same question that the Greeks were thinking about thousands of years ago. How common are planets like the Earth? For anyone who's familiar with the Drake equation, the Drake equation is basically a rubric for working out, you know, how many intelligent civilizations there might be in the galaxy. And one of the important factors in that equation is how many Earth-like planets there are in the galaxy. So Kepler was trying to measure one of these terms in the Drake equation. How common are Earth-like planets? Now, when you look at this plot, you might see a problem, which is that we didn't discover anything like the Earth. This drop off here, so you can see that you get more and more and more planets as you go down here, and then it drops off again, and you see this kind of diagonal here. This diagonal is basically due to the sensitivity of the spacecraft and how long we observed for. So this cutoff isn't real. We don't believe that there are fewer planets here than there are here. It's just that we don't have the sensitivity to detect them. And the reason that is, NASA sends a $700 million mission up to try and measure this, and we get it wrong. The reason is stars are noisier than we think. So we had never measured stars with this, you know, parts per million precision before, except the sun. The sun was the only star we would be able to get this kind of photometry over and over again. And we went back to Giordano Bruno and Galileo, and we were like, the star's not special. Our sun's not special. So if our sun's just a boring, ordinary star, it's probably average in terms of its noise. So half the stars in the sky should be less noisy, and half the stars in the sky should be more noisy. But on average, stars should be about as noisy as our sun. So we designed our telescope. So 1 meter was chosen very specifically, and a 4-year observing mission was chosen very specifically on these assumptions of how noisy stars were. And it turns out when we launched Kepler and went and got the data, stars are noisier than we thought. Our sun is actually anomalously quiet. So instead of it being in the middle, it's on the quiet end, and actually 70% of stars are more noisy than the sun. What that means is that if this noise, if I go back to this data here, so this is the noise, basically this spread. If that noise gets too big, then these tiny transits like D here, if this noise gets too big, you just can't see the transits anymore because the star is too noisy and you're not being able to see the transits. So unfortunately, we're still kind of answering this question. If you extrapolate, which is dangerous, so if you say, I think this increase in planet number continues out, and I think this increase in planet number continues down, then you can extrapolate into this gap, which is always dangerous because there might be interesting physics that's happening about, temperature or density changes that create features that aren't just a normal like power law that you can extrapolate. We can extrapolate, and if you extrapolate, then something between 20 and 50% of stars like the sun have a planet like the Earth. 20 to 50%. That's half the stars like the sun. There's 10 billion stars like the sun in our galaxy. So if half of them have planets, that's literally billions of Earth-like planets in the galaxy. And that's not something we could say 10 years ago. Certainly not something that the Greeks could say 2,500 years ago. But, you know, our best guess now is there are in the billions of Earth-like planets in the galaxy, which is pretty wild. As I've explained, though, there's a few caveats there because we don't actually have any detections. We're extrapolating, but you know, you do the best you can with the data that you have. So what did we find? This is Kepler 452b. I'm sorry about the names. They all have garbage names. I don't get to actually decide the names. They're all named after the mission that found them. So this is Kepler 452b. It's orbiting a star like the sun, which is good. That's the kind of thing we were looking for. It's the right distance from the star to have liquid water on the surface. So it's in the habitable zone, what we call the habitable zone. So that's good. It's about 1.5 to 1.6 times the radius of the Earth, which is starting to get a little dicey. Once you get too big, when you're forming, you're going to gather more and more gas and more volatiles. And you might just not be like a rock with a rock surface and liquid water and then the thin atmosphere. And so one of our open questions right now is how big can a planet get and still kind of look like Earth, still kind of have rock and ocean and a thin atmosphere. So this is on the edge. About 1.5 times the size of the Earth is on the edge of what might still be really Earth-like, or maybe something completely different. So that's kind of borderline. So for a while, this was our best Earth-like planet that we'd found, until something else happened, which is that we realized, this is science in action. You get to see how the sausage is being made. We were really excited about this. And then we realized that the transit signal that we were seeing synced up really well with an instrument artifact in the telescope. So instruments make their own noise, which is separate from the star noise. And the transits that Kepler 452 make look exactly like the signals that the instrument systematic puts in the data. So it might not be there. It could be real, but it could be one of these glitches, basically. The telescope glitches regularly, and this is exactly at the period of that glitch. So this is as close as we got, and it might not be real. We give it about a 50-50 chance of being real. Okay, it's not all doom and gloom, though. We have found truly rocky planets in the habitable zones of their stars, but the stars aren't like the sun. So this is Proxima C. This wasn't actually discovered by Kepler, but it joins the story because it's a hopeful rejoinder to Kepler 452b. This is Proxima C. So Proxima, I'm sure most of you know, is the closest star to our solar system. Here's Alpha Centauri A and B in the background. It's a triple system. And this is Proxima Centauri B. We think there's a C. We're actually debating it right now. But anyway, this is Proxima Centauri B. It's a rocky planet with the right temperature for liquid water around an M dwarf. So remember I said before, TRAPPIST-1 was an M dwarf. It's one of these small, cool red stars. Now, they're so cool that you can actually get much closer to them without getting too hot for life. So, you know, these planets actually have orbits of just a few weeks, like 2 weeks, and it's the right temperature for liquid water because the star is so cool. The problem with M dwarfs is they put out a very different radiation profile than our sun. And in particular, M dwarfs put out a lot of high energy radiation. So things like UV and X-rays, the sorts of things that are actually really damaging for life on Earth. Like if you go out and get too much UV, then you've got a bad sunburn and you might start mutating. So we're not sure. Basically, it's still an open question. Are rocky planets that are the right temperature for liquid water around M dwarfs habitable? That's a really big question that we're trying to answer right now because it seems like they're very common. So if they're habitable, it means that our habitable real estate in the galaxy is even more than just those rocky planets around the sun-like stars that we hope are there, but we haven't detected yet. It would be really great if these were habitable, but we just don't know the answer yet because they get so bathed in this high energy radiation, they might just get sterilized by their star. So we've actually found at least 7 of these, and these are the names. There's Proxima Centauri B that we talked about. Here's the TRAPPIST-1 system. 3 of those rocky planets in TRAPPIST-1 are in that habitable zone or in the right temperature range for liquid water. There are a few that Kepler contributed. So Kepler 186f is Kepler's probably most likely habitable planet. There's also Kepler 442b, and then an additional planet that was found around this M dwarf. So they might be Earth-like. We just don't know. So what we know for sure is that we don't know of anything exactly like the Earth, which is what Plato and Aristotle were arguing about, right? Like is there anything out there exactly like the Earth? So we don't know yet, but we're hoping to know soon. Okay, that's a bit of doom and gloom. So let's talk about all the amazing stuff we did find. So let's talk about hot Jupiters. So this is this class of planet that Otto Struve predicted. Now, what happens if you take a gas giant like Jupiter and move it right next to a star? So it's literally heated up to thousands of degrees. The surfaces, the atmospheres of these planets have things like liquid iron rain because the iron has been vaporized into droplets that's raining out. And liquid glass, the silicates have been heated up and vaporized. So this is actually an animation of HD 1897333b. Again, sorry about the names, getting blasted by its star. So it's so close to its star that it's, getting all of this radiation. And then its star has a coronal mass ejection, burps out a bunch of material. The material blasts by the planet. So this is going to be the CME, the coronal mass ejection. There it is. And then what that does is strip away the upper atmosphere of these planets. These planets are just being vaporized by their stars. The upper atmospheres are just getting ionized and streaming away. They're just getting roasted. So that's hot Jupiters. We've also found lava worlds. So if I show you, so these are Earth-sized things. This is 1 times the size of Earth, orbiting in less than a day. This is like 11 hours. This is a really, really small amount of time that these rocks are going around. And what happens when you heat a rock up to thousands of degrees, it becomes lava. So these are actually like blobs of magma floating in space because they're so close to their star. So this is an animation of a lava world called Kepler 10b. It was Kepler's first rocky planet, and it was our first proof that we had the precision we needed to see rocky planets. So this is a rocky planet orbiting a star like the sun, but the orbit of Kepler 10b is 20 hours. So it's going around its star every 20 hours. And what you can see is this substellar point here, the part of the planet that's facing the star, is just blasted. It's just literally thousands of degrees. So it's melted rock. And then you can see as you go to the terminator, which is the part of the planet where it goes from night to day, the rock starts to quench and basically become glass on the other side. And this cloud of stuff that we're going through is, again, this like silicates being blasted off the surface of this rocky planet. And we're going to go for a little bit of a dive. If you get seasick, you look away for like the next 10 seconds. This is just an artist animation. All the data that we really have are those brightness measurements. So you can take those brightness measurements at multiple wavelengths, which tells you a little bit more about the planet. But all of this is just, our understanding of physics. And if you take a rock and heat it up to 1200 degrees, it's going to melt. So this is Kepler 10b. This is Kepler's first rocky planet. Okay. So we did find more rocky planets that are just, too cold to be lava worlds, but too hot to be habitable. There's a whole bunch of those, which we're learning lots about, like what different kinds of rock that they could be. I was at a conference last year in July. This is going to be a segue, but I was at a conference last year in July, and this Laura Kreiberg, a postdoc, got up and showed us proof that this planet that she'd been looking at was made of basalt. Like, she managed to reverse engineer from the light curve data that this rock had to be basalt because of the way it reflected. And it was just like, that blew my mind, the fact that you could use such oblique measurements and come to this conclusion that it had to be basalt. And basalt, that's just like 90% of the volcanic rock on Earth is basalt. So this is just another rock out there, just, kind of like Earth. It's wild. Also means it must have been molten at some point for it to be basalt because it's a volcanic rock. Anyway, that's an aside. We also found plenty of like Uranus and Neptune sized things, these ocean worlds and ice giants. So in our solar system, I'll show you there's a gap between Earth and Neptune. And what you see is the biggest density of points here, the biggest glut of points is between Neptune and Earth. What are they? We don't know. This is a current big question in the field. So we call them super Earths because they're bigger than Earth. So in our solar system, here's our planets: Jupiter, Saturn, Uranus, and Neptune. So there's a bit of a gap here between Uranus, Neptune, and Saturn. That's about a factor just over 2. But then Earth is 4 times smaller. So you see this huge size gap. And now we're down at rocky planets. And there's Venus and Mars and Mercury. So this is all the planets in our solar system to scale. And what we're finding is that the most common kind of exoplanet, the one that we're finding everywhere, is a super Earth, something in between. The reason that's so interesting is because we don't know what they are. We don't know whether they're big rocks. We don't know whether they're small ice giants. We don't know whether they're something that we don't have in our solar system. For instance, people suggest maybe water worlds, like, you know, that they're made of huge fractions of water, but they're much larger than the Earth. So there's all of these ideas right now. What could they be? So like hot Jupiters, this is like a brand new class of planets that we just hadn't expected, because before we knew about exoplanets, we were so blinkered by what we had in our solar system. And what we had in our solar system was little rocks, big gas giants, big ice giants. And now there's these intermediate things that seem super common. And if they're so common, why don't we have one? So I don't know if you guys have had a talk about Planet 9 yet, which is this putative additional planet in the outer solar system that was proposed a couple years ago now to explain some alignment of Kuiper belt objects that we see. But it is proposed to be a super Earth. You know, if it's out there, it can't be too big, or we would have seen it, but it needs to be big enough to have a gravitational tug on these Kuiper belt objects. So it could be that Planet 9 is a super Earth, which might fill in this gap that we have this strange, the most common kind of planet we don't have in our solar system. So yeah, super Earths are really cool, and we don't know much about them yet. Okay, seeing double. So if I was there in person, I'd ask you to raise your hands and tell me who recognizes this shot, but I'm not. So I'll just give it away. This is Tatooine. This is Luke Skywalker's home world. This is this first Star Wars movie in the 70s. So decades before we knew of actual exoplanets, this existed. You know, people filled in the gap between the Greeks and the real discovery of exoplanets with a lot of fictional planets, and Tatooine is a classic. One of the things that makes it so interesting is it has this double star system, right? And we did it. We found planets orbiting double star systems. So Kepler 16b was the first one, and now there are a few dozen now planets orbiting binary stars. So for this to work, the stars have to be pretty close together, orbiting each other in just a few days. And the planets have to be far enough away that they can basically treat the binary star as like a point source in terms of gravity. There's some instability limit where if they get too close, they're not going to be able to, you know, orbit without chaos, and they'll get flung out. But we found all of these systems that have two stars. And for me, the most exciting thing here is George Lucas, decades before we discovered planets, he even got the colors right. It's a yellow star and a red star. And they're almost always yellow stars and red stars. He didn't get the sizes right, but again, he was inventing this world. So this is actually something that's come true, that we found planets around that binary stars. Another thing that's very different from our solar system that we've discovered is really, really crowded systems. So these planets around TRAPPIST-1 that I showed you earlier, they're all orbiting with periods of just a few weeks. It's like, I'm going to get the numbers wrong, but it's like 2 days, 3 days, 5 days, 8 days, 12 days, 18 days, 24 days. They're all really, really, really close together. Now, remember that Mercury in our solar system, the closest planet, has a period of 87, 88 days. It's within all seven of these planets are within like half the distance of Mercury. Just think about how packed that is and how stable it has to be. So what happens is these planets are almost always locked in a resonance. So their periods are related. So like the Galilean moons, 3 of them have the 4 to 2 to 1 period ratio. If you measure their periods, we find lots of systems that have these that, you know, are very dynamically packed, we call them, because you couldn't put another planet in here without destabilizing the whole thing. This is as packed as it can get and still be viable. And they're almost all in resonances. So I wanted to talk a little bit about K2-138, which is this system here. I'm going to start playing this. I should have asked if this was going to work. Can you guys hear sound?
Faintly.
Okay, let me turn it up.
Better.
Okay. So what's happening is, this is K2-138 is the star, and it has 5 planets. Well, actually now we know it has 6, but when this animation was made, it had 5. And the 5 planets are all in resonance, and they're all in a 3 to 2 resonance. So for every 3 times this planet goes around, the next one goes around twice. And for every 3 times that planet goes around, the next one goes around twice. But the 3 to 2 resonance in music is the perfect 5th interval. So basically, if you turn the frequencies of the planets into music, it actually doesn't sound too bad, because it's in resonance. It's basically playing chords, which is just such a fun idea that these planets are out here like in resonance making music. The other really exciting thing about K2138 is that it was found by citizen scientists. So that brightness data that I showed you earlier for TRAPPIST-1, we have literally decades and decades and decades of this stuff. And we write computer algorithms to go through and look for the dips. But actually, the human brain is the best thing at pattern recognition. And I can teach you in 5 minutes how to find a transit where it would take me 3 years to write the right algorithm for a computer to find that same transit. So citizen scientists going through the Kepler data on a project that I helped lead a few years ago found this system, found this resonant 5-planet system. And I wanted to advertise. So I'm about to describe a mission called TESS. And the TESS data is going to a website called planethunters.org. So this is a citizen science project that's supported by scientists around the world, where you can go and help us find exoplanets. You can go and look at the brightness data and help us find dips. And there's already been test discoveries using this portal. So if any of you guys are interested in finding your own exoplanets, so for instance, when I was lucky enough to get to publish this paper on K2138, we included 5 citizen scientists on the author list of the published paper because they'd helped find this planet, find these planets. So yeah, if you're interested in citizen science, especially, you know, everyone's trapped at home trying to think of something different to do. It's a great school project with kids because again, it's pretty straightforward. You just look at the brightness data and look for dips. Give it a try and let me know if you have any questions. All right, how am I doing for time? Yeah, I'm good. Okay, so the last thing I'm going to talk about is the NASA TESS mission. So as I said, Kepler ran out of fuel in 2018, which was sad. Everybody was sad. But something else happened in 2018, which is that the NASA TESS mission launched. So where Kepler was a single 1-meter telescope that searched one 10 by 10 degree field of view, the TESS mission is 4 10-centimeter telescopes. Each one has a camera that observes a 24 by 24 degree field of view. So the Kepler field fits in like one of these quadrants. So what TESS does is it observes this big, you know, orange slice of sky for a month. And then it turns a little bit and observes the next bit of sky. And then it turns a little bit and observes the next bit of sky. So basically it spends 1 year doing the southern hemisphere and then 1 year doing the northern hemisphere. And now it's 2020, 2 years later, it's just gone back down to the southern hemisphere to start again. So where Kepler looked at one small patch of sky very deeply for 4 years, TESS is doing the whole sky, but very shallowly because they're only 10-centimeter telescopes and it's only sitting on that patch of sky for 1 month. So there is some overlap at the poles. At the equatorial poles, this camera here basically just spins around this point. So the stars up here get observed for nearly a year, but most of the stars only get observed for a month. But that's still the whole sky, which is, you know, that's 4 pi steradians. That's a lot of stars. So TESS is predicted to find an additional 16,000 planets. So remember I said right at the start, we now have 4,000 planets, and that's after 2.5 decades of discovery. We've managed to eke it out to 4,000. TESS is predicted to vault us to more than 20,000 in just a few years. And then you can see that exponential rise that I talked about is on track to keep going. The next mission I wanted to talk about is the NASA WFIRST mission. And just to continue the Star Wars homages, this is the beauty shot. That's what they call it. The beauty shot they made of WFIRST has it coming in like a Star Destroyer. So the WFIRST mission is a 2.4-meter telescope that's going to launch sometime in the next decade. I refuse to give a number because James Webb has burned so many of us on numbers. It's going to launch sometime in the next decade. And it's got 2 main goals. One of them is dark energy. I don't know if you guys have had a talk about dark energy, but it's a very elusive astronomical mystery right now. What is dark energy? And the other half of its mission is exoplanets. So it's actually going to do a microlensing survey of the galactic bulge. So microlensing is a detection technique that I haven't really touched on, but basically it relies on the fact that bodies with mass bend light around them. It's the theory of relativity, Einstein's relativity, and that if you observe a background screen of stars, if stars with planets pass in between you and that background screen of stars, they'll bend some of the light towards you and magnify the background star. So WFIRST is predicted to find something like 100,000 planets. So where is WFIRST sensitive? So here is this this red stuff is the stuff I've shown you before. So you're kind of familiar now with this kind of blob of planets with this diagonal sensitivity cutoff, and here's the Earth. So here's those inner solar system planets again, just to reseat you, that's what that earlier plot was. And this is kind of, Kepler just, you know, didn't quite get to Earth. I mean, to be real, it didn't quite get there. This red line is generous. And W first, microlensing is actually sensitive to planets further out that are well separated. So W first will actually help us complete the census of, solar systems out there around other stars. So here's the rest of our solar system planets. And ideally, if W first is sensitive and you have this overlap region, you can connect these pieces of this puzzle and really get the full picture of, a full census of planets in our neighborhood. So that's going to find, we think that's going to find something like 100,000 planets, which means that actually for the next decade, we're still on track to reach those milestones that Eric predicted a couple of years ago. So we are on the way to finding 1 billion of our nearest neighbors. Unfortunately, as I've said, most of the ones we've found so far are not friendly. They're either molten or they have, temperatures and pressures of thousands of degrees and thousands of bars. So that's not great. But hopefully, the goal is we still want to do this. This is still our holy grail. We still want to find planets like the Earth. So how are we going to get there? This is the last thing I'm going to talk about. It's like we're stuck again. It's like we know what we want to find. We want to find planets like the Earth. We just don't have the equipment yet. But unlike the Greeks a few thousand years ago who knew what they were looking for and didn't have the equipment, we actually have a plan. So this is real data. This is a system called HR 8799. This is the star in the middle has been blocked out by a very exquisite instrument called a coronagraph. And there's 4 planets that are orbiting this star. Now, these planets are all very big, bigger than Jupiter, and very warm. So they're actually, what you're seeing is basically the planets glowing. So this is not really a system like our solar system. But in terms of directly imaging, which is another detection technique, directly imaging planets, this is the current state of the art. And this is amazing. This is literally, we're watching these planets. This GIF takes about 7 years. This is 7 years of orbital rotation of planets around another star. That's wild. That's so cool. We can see planets moving around other stars. But this is kind of where we're stuck now with these really big, really warm things. And that's not what we want. We want Earth. But now we have a plan. So we're going to try and get there. This is NASA's EXO mission swoop, we call it. So this is like the history of NASA missions that have observed exoplanets. So I've talked about Kepler. I've talked about TESS. I didn't talk about James Webb much because that's going to do more characterization than detection. And then we have W first, which I mentioned. In the future, so Tom mentioned the astronomy decadal survey. This is the thing that defines what our priorities for the next 10 years will be. And up for consideration in the next decadal survey, which is happening right now, that's been affected by the pandemic, but it was supposed to come out this year. It'll probably come out next year. Are several missions, several huge, big, pie in the sky idea, great observatory missions of how we might be able to observe exoplanets. So the 3 of them that are considering exoplanets are called HABEX for habitable exoplanets, LUVOIR for the Large Ultraviolet Optical Infrared Telescope, and OST for the Origin Space Telescope. So these are 3 huge concept missions that we've spent a lot of time over the last few years designing to find exoplanets. And the goal is, so this is the state of art right now. What we want is something like this. This is what we're aiming for. We want to be able to block out the light from a star like the sun and be able to see Earth. We want to see the photons coming from that planet. We want to be able to spread that light out into a spectrum and look for biosignatures. We want to be able to observe its rotation and see if we can glean anything about oceans and continents and land masses, polar caps, all these kind of interesting things that are so difficult to infer if you can't actually see the planet. So this is what we're aiming for. So unlike the Greeks, who thousands of years ago had ideas but were stuck, and they got stuck for thousands of years, it literally took us thousands of years to discover Earth. We're not stuck. We have a plan. And I'm really excited about what the next decade or 2 could look like at NASA. And I'm hoping that, the next time I come and talk to your club, I can tell you that one of these amazing concepts was chosen and that we will observe Earth sometime in the next 20 or 30 years. And that's what I have. Thank you very much.
Thank you, Jessie. That was an amazing talk. Terrific visuals. I can see why they invited you to give a talk. Decadal survey. That was just amazing.
Thank you so much. I see there are questions. Would you like to moderate or should I go into them?
Sure, help yourself. Go ahead.
Okay. Why do smaller stars emit higher energy photons? That's a really good question. It basically has to do with different zones inside the stars. So there's convective zones and radiative zones. And it has to do with the magnetic field of the star. So our sun has a big magnetic field that switches every 11 years. And our sun is just kind of big and boring and middle-aged. It doesn't really do much. When our star was young, when it was very young and it was forming, it also was putting out a lot of high energy radiation. A lot of them come from these coronal mass ejections, and it's basically just, it hasn't settled down yet. So the smaller stars just never really get to that point of settling down. They're always active. There's always many more spots, star spots. I always think if I was an astronomer on one of these rocky planets around M dwarfs, like it would be so interesting because stuff would be happening on the star all the time. You know, we're here on Earth with our H alpha filters, like, oh, there's one tiny spot, yay. But these guys would be seeing spots all the time. So basically it just has to do with the physics of the temperature and the layers inside the star as to why it's more active. Did you want to follow up, Michael, on that one? Or I want to give people a chance to make sure I answered it. Okay, I'll go to Derek's question. Why are we assuming that life needs to exist on Earth-like scenarios? Surely there are many situations where life can exist in places where it's not Earth-like. That is a huge question right now. So it's interesting, right? We have to ask NASA for a lot of money to do these things. And I'd love to look everywhere for life. I'd love to look on every single planet for life of every kind of life, but they won't give me money to do that. When we're doing science, we're trying to, a lot of the times we're trying to take incremental steps. And the only place we know life exists is on Earth. So that's why, in terms of a safe bet of spending hundreds of millions of dollars of taxpayer money, we want to look for Earth-like planets because we know that at least once before they've made life. That's not to say that there aren't people out there who are really thinking hard about, what other kind of chemical pathways could there be that, create the energy gradients that we need for life. Essentially, what other chemistry could you make that could make life? And then maybe you could survive under different temperatures and pressures and different kinds of atmospheres and different kinds of radiation. So there are people, astrobiologists, who are thinking about this really hard. What other kinds of life could exist? But in terms of actually going out and looking for it, a lot of us are thinking, we'll start with Earth-like just because we know it worked at least once. And again, trying to get funding agencies to give you money, you kind of have to show them that you've got some reason to believe that what you're doing is right. But in terms of the parallel with what I spoke about, people have been imagining other kinds of life for hundreds of years. I can't wait to find life out there and see, I'm sure that we're restricting ourselves, right? We did the same thing when we thought all planetary systems will look like the solar system. And we didn't find anything that looked like the solar system yet. So right now we're restricting ourselves. All life will look like Earth life. And that's probably wrong, but we just don't know what else it looks like yet. So we're starting with a safe bet is essentially the answer. But I really hope there's other stuff out there that's much more interesting than what we've come up with. Okay. Will hot Jupiters eventually be blasted away to nothing by their star? Oh, yeah. So most of these planets actually only lose a few % of their mass. So they're quite massive. So, Jupiter does have 1% of the whole mass of the solar system. So they lose tiny bits of their mass constantly. And over the life of the star, it adds up to a few %. What we do see, though, if you get too small, then you're not big enough to hold on to your atmosphere, and it does get blasted away. So a lot of these rocky planets that we find really close to their stars, we think they might have originally been maybe Neptune-sized planets that just weren't big enough to hold on to all of their atmosphere, and the atmosphere got blasted away. So we think we call them stripped cores. We think we do see stripped cores. But the Jupiters are big enough to survive. And then there's something called a hot Neptune desert. So we don't find hot Neptunes. Actually, I'll go back to it. Sorry, I like this question. I'll go back to the hot Neptune desert.
And while you're at it, do we know if some of them have magnetic fields that help shield some of that solar wind? Yeah,
so that's a really good question. Even in our solar system, magnetic fields aren't ubiquitous. So it kind of depends. So this is what I'm talking about. See this kind of carve out here? This is called the hot Neptune desert. So we see hot rocks, and we see hot gas giants, but we don't really see a lot of hot Neptunes. And we think it's because of this photoevaporation, that if they're too small, they just don't have enough gravity to hold on to their atmosphere. And if they lose it all and they become much smaller, they become these little rocks. Okay, so how do I get back to the Q&A? Okay. All right. Adriana, are there different chemical makeups or different formation rates or processes that make these systems so packed in? In other words, why are they packed in when ours are spread out? That's a really great question. So before we discovered them, there were two theories of how planets' systems formed and migrated, basically. One was a very chaotic system where planets, you know, in the protoplanetary disk of dust and gas that forms the solar system, planets aggregated together, created a big ball, and then the planets interacted with each other like a big game of pool or billiards or something. One theory is that in our solar system, Saturn and Jupiter actually switched places at some point. So you get this very stochastic scattering of planets, and they spread out a lot. And some of them get kicked out of the system, and some of them end up, you know, knocked over like Uranus. Like it's a violent kind of early formation of the system. And then you end up with these big spread out systems with gaps and stuff, just because it's been such a kind of aggressive formation mechanism. The other theory was that if the planets were forming and the dust disk was still there, so before all of the dust and gas had gone away, been blown away by the star or collapsed into planets, that acts like a torque on the planet. So it's kind of like sticky, and the planets kind of get stuck in the disk and they lose energy to the disk and they migrate slowly in. And then if they get close to another planet, they lock in resonance, because if they try to keep going, they'll destabilize. So they get in resonance with each other. And once planets are in resonance, they want to stay in resonance. So this planet drifts in through the disk while it's still there, catches a planet. Then those two planets drift in and catch a third planet. Then those two planets drift in, and so on. And then you end up with these chains. So basically, it's these two different formation mechanisms. One happens fairly quickly while the disk is still there. So within the first 10 million years of the solar system, this has to happen. Like these planets have to form and move. And we think that most of the time that we get these chains of rocky planets as compared to gas giants, just because they need to be moving while the disk is still there. Or if the disk goes away or giant planets form very quickly, then you end up with this much more stochastic thing. So these compact resonance systems really gave us a clue that this disk migration was a really important thing to be thinking about, not just like a fun idea that someone had. Okay, how has the Drake equation changed in the past year due to where we found water worlds? That's a good question. So, you know, and 10 years ago, this term in the Drake equation, A to Earth, we didn't know whether it was 0 or 100% or 300%, like every star had 3 Earth-like planets. I mean, if you looked at our solar system, how many Earth-like planets would you think we had, right? Because Venus is the same size, but Venus is not Earth-like. So I would say that the fact that we've narrowed A to Earth down to like 20 to 50%, that's not a huge change, right? Like that's a factor of 2 to 4. You know, the answer could have been 0.00001%, would have been a huge change to the potential Drake equation. But the fact that it's, you know, not that far from 1, you know, astronomically speaking, it's within an order of magnitude. That means that, you know, we don't think the crucial term in the Drake equation is going to be A to Earth, because it's not super tiny. I mean, one of the subsequent terms in the Drake equation, like the fraction of those planets that generate life and the fraction of those life forms that become intelligent, those could be 0.0000001, and we don't know yet. But the fact that A to Earth is not 0.0001, it's like 0.2 or 0.5. That's good. I think we've not completely derailed our chances of finding intelligent life by proving that there's no Earth-like planets. We think they're everywhere. Okay. Since nearly all large planets have moons, wouldn't it be likely that some of these gas giants in the habitable zones of their stars have Earth-sized moons and they can be observed by us? So exomoons is what we call them, have been a hot topic for a long time. When I was a postdoc at Harvard, when Tom was mentioning when I came over from Australia, one of the postdocs that I was working with was the first person to start looking for exomoons in Kepler. It is 12 years later and he has not found them yet. We have one candidate. The fact that planets are super hard to find and then moons are so much smaller again, they're just beyond the current technology right now. So I 100% believe that exomoons exist, since moons in our solar system are so ubiquitous. Like most of the planets have moons. Earth's kind of weird because it only has one. I think that there are definitely rocks around Jupiter-sized planets in the habitable zone that would meet our definition for habitable. Now, whether they suffer huge tides from Jupiter like Io, and they're just like fantastically volcanic, whether they can actually, given the tidal locking, they'd be tidally locked with Jupiter, so one face would always be facing Jupiter, and would they get enough temperature regulation with Jupiter and the sun? It's a fun thing to think about. It really is. But right now, there's just still a little bit beyond our detection limits, unfortunately. Okay. Since red dwarfs are so reactive, have you focused any efforts to search in the mass realm of more stable yellow dwarfs? What masses do these stars begin to stabilize? Yes. So Kepler was primarily looking at sun-like stars. Again, coming back to Derek's question about life, because we were trying to be safe. We know that life exists on an Earth-like planet around a star like the sun. So we were looking for Earth-like planets around stars like the sun. We weren't actually concentrating on M dwarfs because the same problem that I mentioned, we knew that their radiation was very different. But it just so happened that it seems like rocky planets are really common around M dwarfs, so we found them anyway. In between M dwarfs and solar-type stars, there are K dwarfs. So these are like orange stars that are, 3/4 of the size of the sun. And people are starting to come back to the idea of K dwarfs. They're a bit of a forgotten middle child at the moment. Everybody was like all about sun-like stars because of the radiation. And then everybody was about M dwarfs because they seemed like, it was easy to detect rocky planets around them. But then we thought maybe they had too much radiation. So now people are really starting to look at the K dwarfs again, these orange stars, and be like, maybe we should concentrate on those. So I think there's going to be a lot of effort, especially with TESS, because TESS is going to look at so many stars. I think there's going to be a lot of attention paid to the K dwarfs because they're not as active as red dwarfs, but the planets still can be closer, so they're easier to find because K dwarfs are cooler. So yeah, I think there is this kind of middle ground that we're really starting to explore. How common are K dwarfs? So 75% of stars in the galaxy are M dwarfs, and then it's like 10% are K dwarfs, and then 8% are G stars, and then it goes down, and a very, very small fraction are O and B stars. So they're more common than sun-like stars, but not as common as M dwarfs. How many exoplanets have been detected to date by the TESS mission? That's a good question. We have over 2,000 candidates, but actually only 55 have been confirmed so far. So the thing is, these missions, so Kepler and TESS, what they do is they tell you candidate signals. They tell you this star has something that goes around it every 3 days, for instance. What you then have to do is on the ground, use ground-based telescopes to go and look again and predict and say like, okay, if this is real, it should transit now and it should transit that star. And you also get more measurements of the star. Do we really know what kind of star this is, how big it is? Do we know if it's 1 star or 2 stars, like the Tatooine system? There's a whole bunch of additional observations that need to be made to turn the 2,000 planet candidates that we have from the first year or so into the confirmed planets. So that's why that number difference is so high. There's 2,000 candidates, but actually only 55 have been confirmed so far. But that number is just going to keep going up. That's one of the things I do, is turn candidates into confirmed planets. Do folks have any more questions?
It looks like that's it as far as questions. Tom, you want to take over for a moment, and then I'll jump in again?
Well, I'd just like to thank you again, Jessie. It's wonderful.
Oh, my pleasure. Thank you for having me.
Yeah, a lot of kudos coming in on the chat and on the messaging.
Okay. Thank you.
Okay, I'll hand it over to Gordon now.
Okay, Jessie, thank you. Thanks a lot. I think I'm going to be sleepless tonight as I keep thinking about your presentation. Fantastic. Thank you very much. Next meeting is going to be August 21st. Same sort of format like this. Guys, you can go on the internet, you can go on YouTube, you can look at documentaries, but sometimes it's old stuff. Here, your club is bringing you up to date the way things are right now. So please continue to join us in, and you get the latest and greatest presentations. And Jessie sure is an example of that. Now, our next meeting is going to be on August 21st, a Friday again. And the main presenter will be Babak Tafreshi. And Babak is an author and well-known National Geographic and sky and telescope photographer of the night sky. He'll be joining us from Boston. We don't know exactly what topic he's going to be talking about, but of course it's going to be interesting. He needs to decide on which interesting topic he's going to focus on. And Claude, thank you for your member presentation. And again, please, anyone has any inkling to give a member presentation, please get a hold of me. Hit that president button in our online website. Today looked like we had 71 attendees. And remember that everyone that has previously received the link to our meetings, previous Zoom meetings and this one, are on our list of attendees that will be notified for the next meeting come August. If you know someone who's new who is not on the list that wants to join in, they have to ask Tom, the website or vice president link at VP at EVAC Online. That's VP at evaconline.org. And then Tom will put you on the list so that you'll be notified and you'll get the link for our next upcoming meeting. I'll just bring it up right now, just so everybody knows. Our usual meeting dates are the third Friday of every month. But in October, it's actually the fourth Friday, because when we had our general membership meetings in person, there was a conflict in the library. We decided to work with them, change the October meeting from the 3rd to the 4th. And since people may have been updating their calendars on that, we thought, well, even though there is not going to be a conflict with library meetings, we thought we would keep that date just because people may have already scheduled on their calendars that that's when our meeting is. So I'll be reminding everybody in our next meetings that usually it's the third Friday of every month, starting at 7:30, but October's is going to be on the fourth Friday, which is the 25th. So that's all that I have. Tom, any final thoughts? Jessie, any final thoughts, either one of you?
Just
Thanks
one
again
comment.
for having me.
Yeah.
One
I put
comment.
the link to the planethunters.org in the chat if anybody wants it.
Good, thanks for that reminder.
Thank you, Jessie. And I'd like to thank Tom Plakis for suggesting that we invite Jessie. It was a wonderful suggestion. And as you mentioned earlier, Gordon, I do have a list of people that have said they're interested in attending the Zoom webinars. And that list is up to about 165 people right now. So every month while we're still in social distancing, I'll send the notice out to those 100 and so many people. And those who want to register for the meeting can do it.
All right, great. Guys, everybody stay safe. We want to see you in person when things open back up. Again, this club is functioning, it's running. Your leadership team is making sure that everything is still running and the bills are being paid. And Tom doing a great job getting our online meetings all scheduled and put together. So I will give a countdown, ending this meeting. 5, 4, 3, 2, 1. Goodbye.
Bye, everybody.